response. Okay. You see why there is a lot to talk about. My main topic today will be the auditory processing and the I used to put that into two bits: the basic processing and the higher processing, which separates a little bit the split between the brainstem and the cortical processing. But here I'm going to summarize all of that, and I will show some examples of temporal coding, neural coding, population coding, and some ideas or some recent developments in that area, in order to give you an impression what auditory, well, how sound is actually processed in the auditory brain. I think this is a very important and interesting aspect for us. That's why I spent a bit of time on that. I will talk a little bit about the auditory cortex. That's a little bit more descriptive, and about the morphology, but not in too much detail. And I will also go a little bit into auditory aging, but not too much from a physiology perspective, but more from a general overview about the aging process. For two reasons: because it is just too much. You could have a whole lecture series on the physiology of that, which I can't do in this short amount of time. Okay, let's just jump right into the where we left it off with the coding in the auditory nerve. We have talked about a number of codes already without actually naming them that. And these are specifically the place coding and the time coding. What we want to know is, if I have a representation, a neural representation in my brain, how do I perceive it? Or in other words, if I hear a sound, how is it represented in my brain, and how do I make sense out of that? Now the simplest thing in terms of hearing, or one of the most important things, is the hearing of frequencies. You can think about a PTA. That's not necessarily a very physiologically relevant example, because these are pure tones which are not necessarily very natural codes, but it still is the question of how do you actually hear frequencies. And the one way we already talked about frequency is, of course, the basilar membrane and the representation of different frequencies at different places of the basilar membrane. That is a very straightforward code. It's the same code as in the eye, for example, or on the skin. If I feel something here, I know that it is next to here, and I have a representation in my brain that tells me what happened from the outside world to my inside, to my brain. And on the basilar membrane, if I have an activity here, I know it is 500 hertz, or 1000 hertz, or 2000 hertz. This is what's called a tonotopic map. Tonotopic means frequency aligned. It means low frequencies on the one side, high frequencies on the other side. Which way around, it doesn't really matter, as long as it is has a neighboring relationship, which means frequencies that are close to each other are always represented next to each other. And that is preserved. That's an interesting fact in the brain. One of the first one that had actually been discovered, that this tonotopic map is basically copied from the basilar membrane right up to the cortex. So if we go into the auditory nerve, then you see that the outermost fibers code all the high frequencies and the innermost code all the low frequencies. If you go in the cochlear nucleus, you find that medial are all the low frequencies and lateral are all the high frequencies. Go further into olivary complexes, or further and higher up to into the cortex, and you do MEG experiments, you see that the low frequencies are more frontal and the higher frequencies are represented more caudal. Interesting question is, how much does that actually tell us about what is that really a coding property? I think yes, it definitely is a coding property, because it always is the rule of thumb. If you know what neuron is, or what set of neurons is active, you get information about the sound. But it's also just a consequence of saving energy, because it's the quickest way of connecting stations together. So that's the auditory, the place coding. That's how we call it, because there's a place of the basilar membrane, codes the frequency, and that is translated to right up to the cortex. Also interesting, almost more interesting, is the temporal coding. And for that I show you a little video, number of videos. No. To show what auditory hair cells roughly do. Can I blow that up? No, I can't. Okay, this is a little bit small. This is supposed to be an inner hair cell, which fluctuates within the fluid on the basilar membrane. And this is a stimulus. It's a pure tone here, sinusoid, and I only show one of the periods. And this black dots means the time. Time carries on. And here it fires. This yellow dot means it fires. But you can see that it fires almost always when there's a high point on the stimulus. And if we do a discharge distribution, or just a histogram, it's called a period histogram, every time it fires you see that it builds up effectively a copy of the pure tone. So it will over time follow the tone, and it will create over time a little copy of the pure tone, of the waveform of the tone. How does it work? Well, obviously the hairs, the stereocilia, are bent maximally at maximum amplitude, and therefore you've got the biggest membrane potential, and therefore you get the highest probability of a spike, always at the highest point. This is not precise, and therefore it is a little bit distributed, and so what happens over time is that you get effectively a copy of the signal, but not a copy of the whole signal, because the signal has a negative part, and therefore we say that it is a half-wave rectified version of the signal. So it cuts off all the half waves, and we talked about the spontaneous activity because that shifts it up a little bit, but effectively you get a time synchronous representation of the stimulus. Now this is wonderful. For every engineer this is a little bit like an AD, an analog digital conversion, because now you have, instead of a sound pressure wave, you got a neural representation of exact the times when all the stimuli on the different channels are maximally active. Nope, that one I want. Okay. Yes, the other one was that little video. That's a different representation of the same thing. Imagine the nerve, the auditory, the hair cells fluctuating over time, and you see that it fires from time to time, but not on all cycles. So there are two aspects to that. It does what that's called face locking, because it locks its activity to the phase of the stimulus. So it will, if it fired, it will fire at a maximum of the waveform, but it doesn't mean it have to fire every maximum. It just skips some of them because of refractory periods, for example. So it's bound to skip some of them at higher frequencies. Now that's face locking. Here's a diagram for that again. So if you have a pure tone, and we can imagine that in one frequency channel every stimulus is not that far away from a pure tone, and this is the spike train that follows from that over time. Then you would sometimes it skips two periods, sometimes it skips one period, but it does lock to the maxima. So every time when it fired, it will fire at a maximum. That stops though at here, say roughly above 5 kilohertz. That doesn't work anymore because the nerve fibers are not fast enough, so there's a loss of phase locking, and instead of a high phase locking they will fire at random intervals. So that's the period histogram that we have already shown. This is an important result from cat auditory nerve fibers though. Cat and guinea pig. Cat are the crosses, guinea pig are the squares. There's an interesting difference between that. This is the frequency, so 100 Hertz, 1 kilohertz, 10 kilohertz. This is 1, 2, 3, 4, 5 kilohertz is here. And this is a measure of the face locking, which is called synchronization index. Effectively means if that is 1, means every neuron, every spike would be at exactly the right phase at exactly the maximum. So you never reach that, but you get close to that. 0.8 or something. It's quite a high measure. And this is all over the frequencies. It does go for other reasons. It goes down at low frequencies, but that doesn't matter very much. At 1 kilohertz, 2 kilohertz, still about 50%, but then it drops down dramatically. So here the end of face locking for the cat is a little bit higher. For the guinea pigs, cats are auditory specialists because they hunt. The guinea pigs don't have to hunt. They don't actually have to listen that carefully to their environment. They use sound mostly for communication purposes, whereas cats use it mostly to well, also for communication purposes, but they hear better because they need to listen to their prey, to mice. The most specialist animal in that respect, actually, that I know is the barn owl, which has been an experimental animal for years and years. And barn owls go up to 10 kilohertz with their face locking activity, because there's another reason why that is so important, is for localization. We come to that actually a bit later, but for localization you need an extremely high temporal position, and barn owls hunt just by listening, not like cats. Cats have relatively good eyes. Barn owls have rubbish eyes, but they've got very good ears, and that means they need to hear very precisely. Humans are slightly in the middle between them. They're more like guinea pigs, more than guinea pigs like cats. Cats are better than us. So our cutoff frequency is something here around 2, 3, 4 kilohertz as well. It's not easy to put a direct and exact measure on that. It depends on how you define it. If you say you 50% normalization index or whatever, but if you just remember 2, 3 kilohertz is where it ends for us roughly, that is good enough. That frequency has also another significance. It is for us the end of musical perception. If you go up on a piano, the highest note is, I don't know exactly, it's between 3 and 4 kilohertz. And then it just stops being musical. You can't make music with frequencies up above here. You still hear a difference between pitch, yeah? With the highest 2 notes, you hear that there's a difference in pitch, but this difference perceptible is small, because the only way that you code it, that you perceive the difference, is by place coding, because there is actually a difference in the basilar membrane activity. But for the lower frequencies, on the left side, there's 2 differences. There's a difference on the basilar membrane, and there's a difference in timing. Because of the face locking of your nerve fibers, they will fire very synchronous to the low frequencies, and you hear the difference between that, but not at the high frequencies. Same as for voice, for many elements of speech. Do carry all the important information up to 2, 3 kilohertz, and then there's not such a good way of coding the information there anymore, and that's why we choose to communicate with our important pitch information certainly more down here, and the formant information as well. All the formants are below 2 kilohertz. Okay, as a summary, given nerve fiber tends to fire most often at a particular point in a low frequency tone stimulus. Above roughly 4 kilohertz there is no face locking anymore. That corresponds to the end of musical pitch perception. Above that fibers fires with equal probability. There is no synchronization index. Why that is probably to the reduction in the AC receptor potential, which is effectively an effect of the sluggishness of the stereocilia, because I just can't follow above 4 kilohertz synchronous with the stimulus. Or in other words, we have a maximum capacitance reached. And then frequencies need to be coded by place, but by lower frequencies it may be a combination of place and temporal coding. But details remain unclear, and I go a little bit into detail with that because I find that an absolute fascinating insight into well, one of the best known and understood neural systems in the brain. First of all, we need a different concept here, though, because we always talk about one nerve fiber, but in reality we have thousands and thousands of them, or millions and millions of neurons. And why do we have that many? Because obviously they're doing something together, which is called population coding. And here's a very simple example for population coding, where it is absolutely essential to it's that one, I think. Yes. To understand why we have several. Hope it's not too small. This is a stimulus here in blue, and this is the time. This is now, and sometimes. Okay, this is yellow. Yellow means one of the neurons spikes. These are 8 auditory nerve fibers, and it's quite a high frequency. And every individual fiber can only fire once every so often, like 3 or 4 cycles before it is ready again after a refractory period to fire. And all of them are doing that. But if you look over the whole of the population, so you look at all 8 of them, you get a perfect representation of the stimulus, because one of them will be active at any point in time, but only locked to the face at this point here still, yeah? This is also an effect, as a statistical effect, because even if you have got sluggish neurons, if you've got many of them, you can average the periodicity out. That's why the actual loss of the face locking, or the loss of the musical perception, is a little bit higher than the loss of the face locking of the neurons. You have many, and you can recruit a lot of them to get summary information. Okay, that's what. Well, this is the simple message of what we mean by population coding, or Volley principle. It even has a name, Viva's Volley principle. Guy came up with that, because this is one of the very early examples for that. The auditory system is quite interesting in that respect, because it has been it stands out from all other neural systems like touch or vision or smelling or taste or things like that. Why? Because it works on a different time scale. Hearing works on, well, thousands of hertz. Vision works on tens of hertz. If something moves more than 20 times per second, we don't see it moving anymore. We see it as a film. We see it as a motion. In hearing, you can follow, well, not you, but your neurons can follow thousands of stimuli per second, which means they need to be very, very specialized for this high temporal precision. And so the research in hearing has been different than research in vision. There are about 10 times more people researching vision than there are hearing. And there are probably also 10 times more people studying vision sciences than audiology, unfortunately. There's certainly 10 times more money going in vision research than in auditory research, which of course is a pain, because we believe that hearing is much more important than vision. But that all said, it is still very interesting, and auditory research, although it is actually quite small, has inspired a lot of groundbreaking discoveries about neurons that are all to do with the time element. Because before, say, 1960s, 1970s, people didn't understand that time is a crucial element in neural coding in the brain. So that the time that it takes the spike from here to here, or that the synchrony of 2 spikes from here and here, are an actual very important measure. That all comes from auditory research. And that is because the neurons are so fast and so temporal precise. And the most important example for that is in localization, which I'll talk about in a second. We actually don't need that. This is a summary to show how neurons, the population coding, share the workload. And this is a spectrogram of the sentence, Joe took father's green shoe bench out. Do you know what a spectrogram is? Hope I don't have to repeat that. It's as a function of time, the frequency, and the blacker the dots are, the more energy is in these frequency bands. So it shows the power spectrum. So where at every time where it's black, there is energy in the system. So here between, what is it, 200, 300 milliseconds, there is a frequency energy in the low frequencies. This is quite a broad spectrogram, so you don't see the temporal aspect so much, but you do see the formants of the O, and here's an U, R, E, green, and so on. You see interesting aspects like green. That's called a diphthong, because it's not a vowel as such, but it's a vowel that slides in frequency. And this is just circled in here, because what people have done then here, recording hundreds of nerve fibers and recording their activity over time, well, playing this sentence over and over again and averaging the activity, and neurons with different frequencies, so 400,000 and 4,000. So you can imagine that took a long time, because these are different neurons, and you need to find all these neurons and play the same stimulus over and over. You can't do that, unfortunately, in real time. We would all give our left arm if we had an experimental setup in which we could measure 10 neurons at the same time to the same stimulus and measure interaction, but that simply doesn't exist yet, that technique. Well, I say yet, I'm not sure if it will ever exist, but it would be necessary. That's why it's so difficult to do research in that area, because you always only have access to one neuron at a time. So this is a very incredible, powerful picture, because it shows the response of a lot of them, as if they are responding at the same time, which they don't, because they were actually measured over time. But what you see, if you believe it at least, is there's very similar aspects coded. So in time, where these arrows are, you see that they all respond here at the high frequencies, for example, to the onset of the J. J has a high frequency component, whereas the O is low frequency. J, O. Doesn't work like that. It's much quicker than that. I'm not fast enough, or not as fast as the ear. And you see that as well. The high frequencies come in first, and then the low frequencies, and so on and so on. And so you even see this frequency glide in here, in this circle. So there's neurons. First this neuron respond, then this neuron, then this neuron, then this neuron. So at this moment, this is cochlear nucleus coding stage. None of the neurons knows anything about the stimulus. They just code effectively, if you like, something very similar to the energy of the signal in their very small frequency band. So if you think of how do we make sense out of that? Who's in our brain actually understanding the sentence "Joe took father's green shoe bench out"? Not even understanding. You not talking about words, but just talking about integrating the information. This cannot be any of these neurons, because these neurons have only access to very narrow frequency band. So the stimulus that they listen to individually sounds like because it's only one frequency. So you need neurons above, higher up, we always say in the cortex, that integrate all of the information and have access to all of this information and make sense to the actual sentence then. Joe took father's green shoe bench out. You can then always argue, and I want to make that case that you see the problem in that is that you get from one stage to another. I now tell you, okay, you need a higher stage to integrate the information. But then there's still only neurons responding sort of mechanically to the stimulus. This is purely, well, it's not mechanical, but mechanical in the sense of there's no intelligence in there and no decisions or anything. Now, who in your brain actually listens to the sentence? Is it the neurons in the cortex? Is it the neurons in the cochlear nucleus? Is it the neurons in the cortex? Is it the neurons higher up in the cortex? And you get pretty much lost in the thought process of who's actually doing the listening and the understanding. And because there is no easy answer to that, certainly not one that we have understood. And so it's a bit of a circular argument. And so brain scientists quite often recruit the concept of the homunculus then. Have you heard of that? Homunculus is the little man sitting in the about 4 centimeters behind your eyes and looking out into the world. That's the guy who's actually looking at the world and listening to the world. But what this homunculus actually is not quite clear. Well, it is a summary of all of the brain activity that goes on at the same time, obviously. But at some stage we have to say goodbye of the in terms of coding, to say we code from one representation to another representation to another, and it becomes more complex and everything, but it's still a representation, because at some stage some understanding or context building and everything has to take place. And we are far away from understanding that, surely. Did you hear that the European Union put 1 billion euros into into finding out how that works? Not the auditory system specifically, but part of that. It's called the Brain Project. What else? So they sit in Switzerland, and they've got 20, 30 research groups all over Europe, and they got 1 billion euros to build an artificial brain with simulation of cortical neurons, simulation of peripheral neurons like these ones, and simulating it all and discovering where's the difference between representation and understanding, maybe. Craziness. But yeah, let's give them 10 years and see if something comes out. Meanwhile, in the real world, my favorite topic is pitch. And that's why I want to explain it a little bit. It's incredibly important for speech perception, for speech communication. More important than we give it credit for often, because we don't really hear pitch. It is so automatic for us that we don't attribute it too much meaning. When I say pitch, most people think about music, but in music, obviously, pitch is extremely important. But in speech, it is as well. So a lot of the information in speech is not carried by the words that you say, but by the intonation. As you know, you can say the same sentence in 3 different intonations, and it means 3 completely different things. You know that example? I can't come up with one. Anybody? The child locked the door. You can say it in different things, in different ways, and it means completely different things. Like the child locked the door, the child locked the door, child locked the door. Simple example, but it goes to show there's a lot more information than just understanding the words, but understanding the pitch effectively, or prosody it's also called. Prosody is the low frequency modulation. Pitch is a little bit more high frequency modulation, but they're related. Okay, what's the definition? Pitch is the auditory attribute of sound according to which sounds can be ordered on a scale from low to high. This is in my book has won a number of records on the most useless definitions in the books of science, but it still is the only definition that is undisputable out there. Otherwise, it is quite difficult to define what pitch actually is. But my better definition is it's a sensation which is associated with musical melodies. Because if you do an actual experiment to measure pitch, you always have to go back to musical melodies and not to ordering it from scale. Anyway, here I give you some examples of pitches. And you tell me if that is a pitch. Has it got a pitch? Because that tells us a lot about auditory processing. This is a pulse train. Pulse means it's a click, and it repeats 10 times a second. Can you hear that? Ooh, no, that's not it. Is that a pitch? No, these are 10 clicks per second. You can actually count them if you're really careful. This is 1 second. You can, if you're well trained, you can still count them. Let's double them. You can't count them anymore, but you still hasn't got a pitch, I suppose, unless somebody has very curious eyes. That's not pitch. Let's go to 40. You certainly can't count that one anymore. Has it got a pitch? No. Maybe. 80. I hate that. I can't give you 80. That one has a pitch, yeah? Everybody agrees. Let's go back and you tell me when you lose the sense of pitch. Clearly a pitch. clearly a pitch. Probably a pitch. Probably not a pitch. We lose it between 40 and 80. Actually, if you do it with slightly more complex stimuli, you find out something around 30. 30 to 40 hertz is where the lower limit of pitch is. Below that, you don't hear it as a pitch anymore. What is it before? Interestingly, before it's individual impulses, individual clicks. Yeah. And I can do it with my voice maybe as well. I can't go down that much because my voice is usually, when I speak normally, it's about 95 to 100 hertz. I can go down very low, much lower. I maybe get down to 70 or something like that, but I don't get down to 40. If I did, you would hear individual clicks of my vocal folds, like you see, there's no information in there. So the interesting thing is why we develop, humans, well, communication developed this process of summing individual impulses like these, which are not pitchy and don't have much information, into something which is just faster. It's nothing different, it's just faster, but it has a different quality. It gains a different quality, a quality of pitch. One of the, in my opinion, one of the most interesting stories of evolutionary biology, because it's maybe a little bit similar to in vision. Individual pictures. If I play you 20 individual pictures per second, it gets a different quality. Namely, it gets the quality of a moving picture of a film. You can't follow that anymore. So instead of individual pictures, you measure something like somebody moving along. Here you measure now something like pitch, and we use the pitch to carry information, maybe musical information or just pitch information in the voice. Now here's some examples of different waveforms. All waveforms can produce a pitch, everything, if it is repeated. That's the key to it. We've got here, for example, the pure tones. This is the waveform, just a sinusoid. This is the spectral representation. That means that one pure tone has only one frequency. In this case, I think it's 100 hertz, so it repeats 10 times, 100 times per second, every 10 milliseconds. You can have a square wave. That is a similar spectrum. Has got one the fundamental plus the harmonics. They all have the same pitch. This one is the one that I just played to you, which is a pulse train. Cluck, 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 cluck. Or this is just an example. These all have the same pitch because they all repeat with the same periodicity. They all have the same fundamental frequency. Single pulses, it's just as an example, they have a flat spectrum. They don't have a pitch, neither has white noise. And a short tone is something in the middle because it depends on how long it is before it actually has something like a pitch. Why do I show you that? Because there is an argument how we perceive pitch, and I want to go a little bit into detail of that because there are two different theories or two different mechanisms, and it's still not resolved today what actually exactly happens in our brain. This is an ongoing research area, and the two waveforms that highlight the difference is the pure tone and a pulse train, because they are the opposite side of a spectrum, if you like. Namely, this one is well defined in time, but only has one frequency peak. This one is sorry, the other way around. This one has a very well defined temporal process, but it's not defined in the spectrum at all. Okay. First, the definition of pitch. Everything that leads to musical perception I call pitch. Everything else is timbre. Just if you wonder what timbre is, it is everything that isn't pitch. So if you have a violin and a piano that both play an A major, then they play the same note. They play the same pitch, but you can clearly hear the difference between them. And while you hear the difference, that's the timbre of the sound. Sounds with different pitch can have different timbre, or the other way around. Okay. Now this is the explanation of what happens on the basilar membrane on a slightly abstract level when you hear a complex tone. This is the input spectrum, complex tones. This could either be a pulse train. Let's assume it's a pulse train, it doesn't really matter. And this is the auditory filter banks that we talked about in length. So they become wider. This is a linear frequency axis, so they become wider. Careful with that, because we sometimes put that on a logarithmic frequency axis, and then they actually become sharper at higher frequencies. But in fact, on a linear frequency axis, when we want to understand our frequencies linearly, as we do if we generate them, then the auditory filters become wider. And if we put our stimulus through our filter bank, we get what is called an excitation pattern. So that's excitation in decibel as a function of linear frequency. That is the unrolled basilar membrane, but looked at linearly. And you see two different broad regions, namely one region here at the very low frequencies, where the filter bandwidth is roughly in the order of the pitch of the frequencies of the stimulus, which means that each of these pulses, frequency pulses, so this 100 Hz, 200 Hz, 300 Hz, find their own filter, and so they are what's called resolved, because you actually have one filter for each frequency component. If the frequencies are low enough, they're a bit overlapping, that doesn't matter, you still see a wiggle. And at higher frequencies, obviously, when they're too broad, you get 10 or 15 components in there, and this is unresolved. Now there's a fundamental difference in the perception between the resolved and the unresolved harmonics. That's what they're called, because you can resolve the resolved harmonics. You can hear them out individually if you have a very, very trained ear. Is there anybody here as a very trained musician? No, they would know what I talk about, but if you have 10 years of musical training, you can actually hear these frequencies at the low frequencies individually. As normal mortal people don't do that, but we can do experiments that show that we still have that representation in our brain, but we choose not to have the access to it, if you like, because you need the training to do that. On the basilar membrane now, there's an interesting difference between the resolved and the unresolved ones. On the resolved ones, what you see is in the low frequencies, the basilar membrane just follows nicely the period of the stimulus, effectively exactly that component. On the opposite end of the spectrum, at the very high frequencies, it just follows the envelope of the stimulus. This is the difference between fine structure and envelope. And I want you to listen up, because this is related to the next assignment, because this is perceptually a very important differentiation between fine structure and envelope, which is in research at the moment very, very hot topic. What do we hear? Do we hear fine structure, or do we hear periodicity? Do we hear both? Do we hear a mixture of both? And when are they actually important? There's a number of interesting arguments to be had. One of them is that cochlear implant people, for example, there's a processor, a speech processor, that gives them information. They cannot choose to listen through their basilar membrane. They have to listen to what we give them, and what we give them is the envelope, nothing else. We do not give them fine structure. They do not have any resolved harmonics. They do not have any high wiggly frequencies that are, in any case, any information about faces. They only get the fine structure, like the envelope, like this. And they make good use of it. They can understand speech. So obviously most information is in the envelope, but then there is a lot of information in the fine structure. What do we need that for? More complex things, like localization, for example, is the answer. Now, what happens in between is a little bit of an, well, it's a continuation. There is a transition between the fine structure here and the envelope, which is very much similar, effectively, to the, not effectively, it is very similar to the electropotential of a hair cell, if you remember that. If you play a low frequency sound, it will follow the low frequency sound, the receptor potential of a hair cell. If you play a high frequency sound, it will follow the envelope, not the fine structure. This is exactly the same. But here we split it up into different frequency bands, and you see you get these two different representations, one at the high frequencies of the envelope, low frequencies, period. Okay, now this leads us to the two theories of pitch perception, namely let's just the place code and the temporal code. Let's put a figure on it, or to understand it. Let's say we have 500 Hertz and 550 Hertz, and the two mechanisms that you have at your disposal are the rate code, or the rate place coding. So on the basilar membrane, both of these different sounds will produce different activation patterns, and if you've got very clever nerves, they can tell that this one has a maximum here and the other one has a maximum there. You can see this is not quite straightforward because they're actually quite close together, but it does work. The other and completely complementary explanation is temporal coding. So if you look at the nerve fibers, one of them is a 500 Hertz neuron, the other one of a 550 neuron, then their reciprocals of the intervals are multiples here of 2 milliseconds and here of 1.8 milliseconds, which is 500 Hertz or 550 Hertz. So you got the two completely different mechanisms to code the same thing, namely the pitch of the stimulus. Here's how you could imagine that the place code would work. It needs something else, something that we have learned, namely a pattern. This is easy to understand if you imagine that a stimulus has different. This is a stimulus, for example. This is called a modulated amplitude modulated stimulus. It would have a frequency of 300 Hertz and a modulation frequency of 100 Hertz. And how do we know that this is the modulation frequency? Well, we would need a pattern. We would need a pattern like this, either a pattern of 100 Hertz or a pattern of this one 110 Hertz, and we put that on top of each other, and you see, the 100 Hertz pattern fits quite neatly, because each of the red components is within one of my pattern. It's a pattern matching. Simple as that. And if I use the 110 Hertz template, you see that wouldn't work that well. So you can imagine there is a representation of the frequency somewhere in the brain, and then there is a pattern matcher, and it has all the representations of the patterns, and it tests this pattern and that pattern and that pattern. Sounds a bit artificial, but it turns out this is really not too far away from mechanisms that the brain really uses. Interesting thing about that needs to be learned, because of these things they cannot be genetically coded. It's much too complicated. So they need to be completely started from scratch at birth or before birth. Listening to voices and things develops these templates. That can be shown by raising animals, for example, in complete sound-free environment. They do not develop these templates, and are not able to discriminate frequencies, for example. Okay, that works quite well. However, it doesn't work well at all frequencies. These templates must be learned. That works best at the low frequencies for the resolved harmonics. This can explain the dominance of the lower harmonics. I haven't talked about that. It's a psychophysical phenomenon, that if you have a complex sound like that, then the low frequencies will dominate your perception of pitch. They're the most important ones. This is not surprising, because if I speak to you, for example, the highest components, the highest impact of my pitch comes from all the low harmonics between 100 and 500 Hertz. They dominate your pitch perception. This is just where human speech has its most energetic harmonics. Can explain hearing out harmonics, yes, but it fails to explain pitch perception at higher frequencies, where these templates don't match anymore, don't work, or where no resolved harmonics exists. So this is a nice model, but it only works for a few stimuli. And therefore we need a model for this temporal processing, and for that I show you this 100 Hertz complex tone. This is my click train. This we already saw. This is the movement on the basilar membrane. You have in the low frequencies you follow the fine structure, and the high frequencies you follow the envelope. And the auditory nerve fibers would produce spikes which are phase locked, so we bring everything together, what we heard about. Here you don't have anything because the phase locking is locking to something completely random, but it doesn't matter. Here it phase locks to the fine structure, here it phase locks to the envelope, and if we sum them all up, or what is called the summary autocorrelation of these, you see that that the periodicity is preserved in all of these nerve fibers. So if I just look over all of them and average the most prominent intervals, I will get the pitch with no fail. So that's a very effective way of extracting periodicity. It can explain the pitch perception in most, but not all stimuli. The neural mechanism could be autocorrelation or cross-correlation, and people have in the last, well, certainly since I'm in the field, since the late 90s or something, there has been a lot of effort being undertaken to prove this beautiful theory, because this theory is really, really good. Autocorrelation would explain most of the pitch perception that people have. The problem is there is no physiological evidence whatsoever that the brain actually does it like that. So it's a complete mystery still, and our models are much better than what the brain does. So a lot of people still try today to find these autocorrelation mechanisms. But it is still, although there is no evidence, everybody believes that this is the way that we hear pitch, which is quite fascinating if you think about it. Okay, this is a little demonstration, love demonstrations, to show that the pitch of completely different stimuli, that's what I was talking about, maybe I should have shown that before, can be the same. So this is 160 Hz pure tone. It's an octave. If you're musical, you hear that there's an octave between these three. And let's do the same for the click train. Ah. Now, are these the three the same melodies? No, the melody. You don't have to be musically trained to tell me that. Yes, this is the same melody. These are three the same tones, 160, 320, 640, and they're playing the same octave. Now, these are two different mechanisms, though. Everything I said points to that, although they're the same pitch perception, you can make music with both of these sounds. They sound differently, obviously, but the main percept, the pitch, is the same, but two completely different brain processes calculated for you, without us being aware of that, obviously. But to the best of our knowledge today, the pure tones would be resolved by a periodicity, by a place coding, whereas the click trains would be resolved by a time coding. And we still hear them. They sound different. They have different timbre, obviously, but we still assign them to exactly the same pitch. So, a summary: there are two mechanisms of frequency and pitch coding. One is a place code, so looking just which neuron is active. Good example for that is a sine wave, where the pitch is the frequency, and it works best for sine waves at higher frequencies. It doesn't work well for low frequencies. And the time codes means we measure the time between spikes. And the click train is a good example for that, and works best at low frequencies. No single theory can explain all stimuli, but it becomes more obvious that a mixture of these actually is at work, and our brain selects the best mechanism for the best stimulus at a time. And for the low frequencies, we certainly prefer the timing codes. For the higher frequencies, we certainly prefer the place codes. And here I have, maybe you do that in your own time. I've got 250 Hertz tones, completely different sounds that all should have the same pitch, but some of them are explained by spectral, some of them are explained by temporal pitch. This one now has no pitch anymore. Here's a face locking. It's the same stimuli, just transposed in frequency. Here it works really well, here it works okay, and here it doesn't work at all. Although it's the same stimulus, just transposed in frequency. Anyway, I don't go through that because we need to have a break, and then yes, no. And then we talk about the sound localization after a break, okay? 10-minute break. They have a cochlear. Oh, okay, yeah. And then, because obviously you were saying that they don't have the fine tuning. Yes. Got the envelope. Yeah. They then struggle because they can't distinguish like so. Definitely, they will not hear the pitch. They hear the very broad pitch, maybe 4-5 semitones. They can sometimes discriminate because of the place code. They can do. They have access to the place code, but nothing else. And you will not find cochlear implant person with playing in an orchestra, as simple as that. Could it be because they potentially learn that a certain envelope that they hear is related to certain fine tuning via elimination? People try, not for the lack of trying, because there are many people that have lost their hearing as musicians, and then they suffer because they want to hear their music again. But it is virtually impossible to get any useful information out of that. You hear people that can play completely deaf, and they refer to completely deaf, and they feel the vibration in their head. So if you go to his playing, so once you listen to the vibration, what do you feel is the vibration? That only works for very low frequencies. I'm skeptical of how that works. And if that was the low frequency section, and the high frequency was the envelope. Yeah. I'm skeptical. Maybe she has some residual hearing there. Okay. There's a difference between hearing impaired and cochlear implant, because cochlear implant only have 22 channels, and they are very broad as well, so they have a lot of disadvantages with that. Yeah. But yeah, there's music therapy for the cochlear implants. They're fine, especially the professionals who are simply rhythm. They can have a lot of fun with that. They actually train their hearing. But this is not about the human tone structure and the kind of melodies that we play. They do actually. There's a composer who's doing compositions for cochlear implantees, so they produce music. Everybody loves music, wants to listen to it. So they produce music with big frequency jumps, for example, so that they can follow the system. Yeah. What do you do about it? Diagnose me. I'm going to make sure you do. I've never heard like that. Just makes noise. So your homework for Friday. We have something to talk about. Get a grip on the difference between temporal codecs and bass code, and write a page on how do we hear the two different codes. Okay, we're going to discuss that on Friday. How do we hear different pitches? And we can go into a bit more detail then as well, which is interesting. Topic everyone? I brought my own laser.
Go try and get some free stuff.
Oh my
Oh,
god.
yeah.
She's gonna come and steal candy.
Yeah, that's the only reason she wants to carry on.
And
She get all the
chocolate.
free stuff. Yeah.
Are they gonna ignite them?
No.
They're just gonna give you papers and let you sign stuff.
I'm not gonna sign anything else.
I don't give my autograph.
I tried. We had it. We're like filling loads of forms out in matches.
I didn't do anything.
I haven't had many.
No, me neither.
That means you didn't win anyone. Like all these different competitions. Did you go finish?
Yeah. So it came to the same day. We're like,
I didn't do anything
Nothing.
because I knew
Yeah.
you win. I mean, why are you gonna go to every stand and
What were you doing then? You just sort of
yeah.
lurching around the corners of the venue?
No, I was looking what they had. I wasn't gonna go, give me a stump, give me a stump. There were people that didn't even talk and they came, give me a stump. Then the next one, give me a
What do they
stump.
want a stamp for?
You feel like this thing full of stamps, and then you could win an iPad or I don't know what that. And then everyone was like old ladies like
Yeah.
put me a stamp, put me a stamp. I was like, okay.
We were gonna do it and then we were like
We went to an agent once with STA. I don't know if you know the travel agency. There's STA. And they were like, enter this competition, you might win a free holiday. And we were like the only people in the stick. So we're like, yeah, okay. All of us entered it. None of us won. We were the only people there. How could you not win?
It's always bullshit.
Yeah.
yeah, we tried to win Temporal as well.
Yeah.
Oh yeah,
And then we
that's
back
the
them up.
best thing I did. Yeah. Win it. It's for 2 people, so you should fight. No, you come from there. I'll do that.
Wow. Wild racism.
So I'm used to it from there.
I can be racist later.
Again.
Really?
Yeah.
Sorry, bandwagon.
Not essay. But
Did you
no.
finish Friday?
Yeah.
Did you finish yours? Have
We
you
have
decided to finish
tutorial.
yours?
No, I thought he was gonna be
What?
What's
Alan said you were doing psycholinguistics, but he's not mentioned psycholinguistics.
What?
I don't know what he was.
What in the essay? Why are you talking? The essay?
Yeah.
Who said?
Everyone says something different.
Change our to like cultural or like
Well, zero isn't reconstructible either.
Yeah, I'm not
But
gonna change
I
it
think
now.
we get away with just adding the frequency channel back, which we can also do for the gamma chirp. So at the end, it doesn't really matter because we just add them all. That is computationally extremely cheap.
see corridor stuff.
I think
That little bit manages bloody.
what I can't remember some of
There's faster here on time.
yeah.
And they are also
Oh,
Yeah. They get used to the shift. The shift is not necessarily.
And because mine is back to
no,
the
but
like,
the wrong speaking.
But it's still often the only show that they're correct.
Because your head keeps posting.
They also have access to the envelope. Because what they do is they take the
Otherwise,
function
it's just rotating the camera.
of the signal.
You're having a linguistic.
Otherwise,
goes to the hip.
So you've got in one channel, you've got
That whole
the envelope.
it's just gonna jump off later on.
You've got the function. The processor
Takes only the computer.
Then you're gonna
takes
have
only the
like
envelope and replaces it with
They'll be everywhere. They'll be
periodic clicks, but they are determined by the implant. So they
And then you know she has a very good
depends on the implant. It's 800 hertz usually, but 800 click, 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 click. But they will follow the envelope. So that's the only
Oh my god,
information.
it's awesome.
That is the most important, obviously, by far the most important for speech perception. Because if they've got that in different frequency, they don't really. Michelle down over and over, you only need about 4 or 5 channels to get a good pitch
Oh my god!
Yeah.
Okay.
So that's 22 electrodes, and they're not independent of each other, but in the end they've got like 8 independent channels, and that's good enough.
Does it have smearing as well? So
We've got
it's over
smearing.
But so, but this is where poor place goes.
It's very poor place coding, that's right. But for pitch perception, it's still the best that they have. Because the envelope doesn't really take
You are bored.
Another
relationship.
Well, it does sometimes, I guess. But the pitch perception is usually within
Because the impression I've had is that since they use very poor fine structure orientation, they rely on the periodicity. So the periodic, they can extract F0
Where is it?
the periodic key.
theory they could do that.
So that was my impression.
Yeah, but they're very, very bad.
Oh my god, I was
Zero information that
Yeah, I was like, get out.
So how is there a time coding record on that?
I was
Just the envelope.
Is what you said though?
No, the time coding is rubbish because they don't have any
It was so long.
So that they rely on place coding.
They rely on place code for pitch perception. And for speech perception. Pitch isn't, they don't have pitch information in speech. You listen to the coders, you know how the pitch perception works. It has nothing to do with pitch.
And the patient has to be like
And
relaxed.
if somebody talks higher pitch or lower pitch, it's completely lost on them. Because they only follow the internotes structure. And that has a cutoff of, what is it, 300-400 hertz or something.
Really?
I mean,
why not?
For high frequency.
Oh, you did it?
Normal coding, later.
No, I didn't do it. I wanted to do it. But I was very
Well, they always use a mixture of both, but they don't translate.
No, it just felt weird, like.
Oh, but yesterday.
No, yours is a
Yeah, we were trying to play.
She was like doing like this,
but she had a coat over her head.
So how is place coding? Maybe I understood that wrong.
This means that the time coding is even worse. Sorry, that's not the result harmonics. If you think about the result harmonics, yes, so that higher frequency.
We have to be all quiet.
If you have a single frequency of the high frequency, then the place code is the only exit that you have.
Over that.
If you have a harmonic spectrum, then you cannot be wrong. So there is no pitch
She'd wake up with that.
But in that case, it is again the envelope.
So if you have a filter, let's say, okay, you have a broad filter, and you have different frequencies falling in the same filter.
Yeah. So the frequency resolution is rubbish.
Yeah, so you can already detect the 2 hours delay. 2 hours?
Yeah.
They are on the same filter.
That's right.
So what is it? What's really the time coding?
Time coding is that if you look at the temporal processing, you have signals like that, first of all, it's like that. Yeah, because it has all the components in there, which gives you like something like that, pulse train. Okay? And if you send that through a filter like that, what you get is this. You get the envelope like that, but you do get the envelope. So in the time domain, this is time. In the place domain, you cannot resolve this. You have to use the low frequencies where you have to resolve harmonics for the pitch. In the time domain, you have the envelope. You lose all the fine structure, but you do get the envelope information in there. And this is for normal listeners, this envelope information I can already for pitch.
So one place coding is poor.
Yeah.
Time coding is slightly better.
But it breaks down at 3 or 4 kilohertz. Yeah, that's the point. So that only works even at even higher frequencies of 3 kilohertz. That doesn't work because the time just completely clears. You don't have to fix something, and then you are indeed back to the very poor place codes.
But I think
So that is the reason why if you frequency, the DF, the frequency differentiation limit, is something like 0.2% at low frequencies, and that goes up at high frequencies. At 3 kilohertz or something, you really get worse. So 10 kilohertz, you have a tough time to differentiate any frequencies, because neither time nor place works very well.
Is that proper Apple users? Or
No, that's normal.
so you can start.
Yes, we need to get going. One more. Okay. It was an interesting question because people are always interested in cochlear implants. They are really good models of hearing, but they're the most successful prosthesis that is in use. They give back people good hearing, good speech perception. I was just explaining to what's your name, Josh? Yes. Roughly what the difference between envelope and fine structure is here again, because I think this it will become important for us. If you have one frequency channel, and this could be a stimulus like that, you've got this is the envelope of a speech signal, for example, and this is the fine structure underneath. So the envelope doesn't really exist. What exists is the fine structure. The basilar membrane vibrates very fast up and down. Let's say 2,000 times per second. But here it goes up a lot, here only a little, and so on. So the envelope, theoretically envelope, is obviously there. Yeah. What we listen to, normal listeners, for low frequencies is both. We have access to the fine structure and the envelope. At very high frequencies, let's say 4 or 5 kilohertz, we only have access to the envelope because the phase locking breaks down in between with the fine structure. Cochlear implant users have no access to the fine structure at whatsoever. They only, that's what their processor, their speech processor does, is extract the envelope and then take out the fine structure and replace it with 800 pulses per second. 800 is a Cochlear. That's sometimes a different implant that goes up to 1200 or 1500. Doesn't matter. But the point is, they will only ever get the envelope, and that said, they get the positive envelope, and they replace the fine structure with the regular pattern, so they don't have the access to the fine structure. They still hear speech, obviously, yep. So that's perfectly all right and legitimate to listen to speech. And it has been shown often that you only need about 4 of these in different frequencies. Let's say 500,000, 2,000, 4,000 hertz. 4 channels, you get 100% speech perception. In quiet, that is. In noise, that breaks down pretty quickly. That's the main problem with cochlear implants. But in quiet, that is good. The other problem is it doesn't sound very good. If you listen to cochlear implant vocoders, these you know what is said, but it doesn't sound very nice. So you wouldn't choose to have an implant, but it's better than not hearing anything, obviously. Okay, sorry. Question. It is what? Is sharper. Only yes. You're referring to the Q values, which go up. The higher frequency, you've got higher Q values. So yes, if you plot that on a logarithmic axis, then they have sharper filters at higher frequency. But be careful, this is a log frequency axis. Yeah. Okay. What's the question? Yes, we can't. That's the problem. We can't. It doesn't matter how sharp the filters are. The neurons that attach to the hair cells just cannot follow it fast enough anymore. They break down. Because if remember what I said, they have a pure tone. The simple face locking, you have a pure tone. It's slow, then the neuron will fire here and it will fire here. Chuck, chuck, this is face locking. But at very high frequencies, the neuron will fire, don't know, here and then here again, and no relationship to the face. And therefore you cannot have the fine structure, this is the fine structure, cannot be translated. There is no way of having access to that. Because the filters are broader at the low frequencies, and it's also not because of the noise. It maybe also because it's not very necessary, because you've got the nice temporal coding that gives all of the information there. Okay. Okay. We talked about place code. We talked about time code. I give another code there now, which is time of arrival code, and I see already that I will not get through the end of the lecture, so I've got something else in case Daniel has another hour left or something later on. But this one is important, talking about the sound localization by ITD. Have you heard about ITDs and ILDs? Level differences and time differences? Good, I don't need to explain that. Just short, the time difference, inter-oral time difference, the time difference between if the sound comes from here, will reach my right ear before my left ear, and the time difference translates to can be translated to a direction. This has been proposed already more than 100 years ago, Rayleigh duplex theory. Investigating how that works, though, has taken the better part of the last century, still under the today, but has produced, I think, one of the most beautiful models, certainly in our area of research, if not in all of science, which is called the Jeffress model, that I want to explain briefly, because it has inspired research in that area for the last 50 years, and in other areas as well. So the pathway, the dedicated pathway, comes from the two cochlear, left and right. The cochlear nucleus is where the neurons, first the processing station where the auditory nerve fibers end. From there, there's a direct line across the midway into the contralateral, what's called MSO, medial superior olive. And there it also gets an input from the ipsilateral ear. So here, obviously got an MSO on the left side and on the right side, but there is obviously a connection between the two ears. So what happens there? First, we need to go back a step again to the auditory, to the ventral cochlear nucleus here. This AVCN, it stands for antroventral cochlear nucleus. Ignore that. This just means it's the ventral cochlear nucleus, the first processing station. There are a number of neurons which are called bushy cells, which, this is an electron microscope with the color. This is the cell body, and this is one huge, big synapse. They are only found here, not found anywhere else in the body or in the brain. They're called calical endings, or end bulbs of Helt, I think they're called. So this is the axon that is arriving, covers the whole cell in one gigantic synapse, and then it goes out again into the postsynaptic neuron. What it does, though, this kind of processing, is that it cleans up your noisy signal, if you like, in signal processing terms. This is the auditory nerve response to a pure tone. Don't know what the frequency is, 200 hertz or something, but you see that they are a little bit wobbly. So if you do a histogram, then it is quite distributed around the mean. If you take one of these bushy cells and record it, you see that they are much, much sharper. So they do integrate over not only one auditory nerve fiber, they actually have several inputs, but one is major. And what they do is they not only preserve the timing information, but they even improve the timing information of the spikes coming from the auditory nerve. That's not all that cells in the cochlear nucleus, it's just a subset of them, but important subset, because these cells project to the contralateral side, where they end up in the superior olive with cells from the other side. And what can they do? Does that work? No. Yeah. Aha. Mr. Scruffy. Right. this is a picture of the auditory brainstem, 2 cochlear, and a sound now coming from the front and then from the sides. And this is obviously a model. This is supposed to be the MSO, medial superior olives, and with 7 different neurons. And what you can see is that they're arranged from top to bottom with a special pattern. Namely, that the connection here is a bit shorter than that one. So now observe the sound wave coming from the front, and what we imagine happens. This is the sound wave, click, these are the spikes, and they travel, and they go blah 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 blah. And this is much too fast, and therefore we slow the whole thing down now. So here's the sound wave. Here something happens on the basilar membrane, and the neurons, the auditory nerve fibers fire on both sides at the same time, and send the spike to the cochlear nuclei, where they come to where they arrive at the same time, because the sound was coming from the front. Okay, and now they travel on the right and on the left side, but while the right side is already there, the left side is lagging a little bit. And you see that in neuron number 2, it arrives from both sides. Remember what the neural computation, what I said? That's the coincidence between 2 inputs, and this is the only neuron where the coincidence is at the same time, that both spikes arrive at the same time. So this one lights up, means it fires, it becomes active. That means we can say, neuron number 2 is important when there's a sound coming from the front, because it will frequently light up if the sound coming from the front. Now what happens if the sound comes from the side, like this one, here from the left side? This one responds first, this one responds later, so this one is lagging a little bit. And lo and behold, a different neuron now, number 6, is the one that lights up. So number 6 codes for sound that come from this direction. So the genius about that is that it has transformed a direction of sounds into a representation in the body, a physical, it's not tonotopic, what's the localization topic, representation in the brain. So like a frequency, high frequency to low frequency, you got now left to right.
Did you say the MSO is only on one side?
There's on both sides. You've got 2 of these representations, and the final.
They're happening at the same time.
Yes,
On both sides.
yes, and obviously the other way round.
Yeah,
So
so
the final answer will be a mixture of both. Yeah.
So on a frequency get 2 from, let's say, the right hand side,
Mhm.
and then 2 from the left, so it should be equal.
I'm not sure I understand the question.
So surely, if they're on both sides, they're going to be equal and opposite.
They're equal and opposite, exactly. You've got an MSO here. Let's do it like this way. So you've got a cochlear here, cochlear there, MSO here, MSO there. Let's say this is the midline, and then you've got a neuron. If the sound comes from the front, then both of these light up. If your sound comes from this side, then let's say this one light up and this one lights up. And obviously you need another station then somewhere here in the cloud. This is my homunculus looking at these and says, this one lights up, this one lights up, the sound must come from that side. That needs to be learned then, of course, something like, yeah. And all of these things are actually learned, and nothing is hardwired, because all of these connections, obviously we're talking about, what's the times that we're talking about? Guess, how much time does the sound takes from the left ear to the right ear? What's the minimum, the maximum time difference that we actually can talk about? 6 milliseconds. Other guesses? You're an order of magnitude out. It's 0.6 milliseconds. It's less than a millisecond. So we're talking microseconds, and this is the maximum microseconds. Where are you most sensitive? In front, where you can discriminate something like 3 degrees azimuth, which translates to very few microseconds, 1 or 2 microseconds. There are animals out there, and we've got the picture of that. There is a very good paper out there, although it's disputed these days for other reasons. What are they? Fruit flies. Good old fruit flies again. They can discriminate nanoseconds. between left and right because they're so small. Obviously, the smaller your head size, the less time difference you actually have. So, that's a fascinating model. Comes from 1948, has inspired people for decades. Delays. Secondly, physiology has inspired people to look for these delay lines. That's what we need. So the three parameters that we need here, the three assumptions. We need this coincidence detection. Neurons need to be working like that they fire more often when they get input at the same time. That we all believe is true. Secondly, we need these delay lines that we were talking about. So they're coming from the right ear, it takes a bit longer than from the left ear. And thirdly, we need a tonotopy because we need to connect the same frequencies on the left ear and on the right ear, otherwise everything would go haywire. Now, lo and behold, people have looked for these things physiologically and found that 1 and 3 are true. But 2, it turns out, in the last 5 years or so, only in barn owls. Funnily, people did these experiments for years and years in the 80s. This guy called Konishi done these experiments in the barn owl, and he found these delay lines, and they still think that they are there. And people have repeated these in mammals for ages and could not confirm it. And I'm not going into detail because this would be a very interesting lecture in itself, but it turns out that mammals, so us, now everything that I said is relative, do not use this mechanism. Apologies for why do I tell you that, because it is such an inspiring model, and it obviously has been is used in birds and in lizards, but in mammals it isn't. That tells us a lot of things. Firstly, that we're evolutionary, very different animals. Secondly, there are different solutions for the same problem. And we know very well which solution, the engineering solution. This is an engineer. Jeffries was an engineer, and he thought, how would I do it? If I played with these things and put them together, this is how I would solve sound localization. And it turns out that birds indeed do it like that, and lizards. And then everybody thought, yeah, we've solved the problem for 20 years. And they were carrying on looking for these delay lines in mammals, and they're still not found. I might wager a bet they don't exist. So we have a completely different mechanism, which is very poorly understood at the time of writing. There are some good ideas for it, but there is still a bit of research to be done, which doesn't work on the delay lines. So this is as a warning for you, don't believe your lecturers. If I tell you the nice, great models, they're usually wrong. Models, do you know the saying, every model is wrong, but some of them are useful. Jeffries' model is useful because it inspired loads of people to go into that area and do research, but it is wrong, like any model, to a degree. And right to other levels, probably, as well. Yes. Sorry, did I confuse you a lot now? I hope so. Okay. Here's my last example, coding by time or rate. Rate coding. Haven't really talked about rate coding. This is a special aspect of the place coding. If you look at place coding, so looking at which area of the basilar membrane is active, you need a certain time to actually count spikes. Yeah, that's called rate coding because you measure the rate of the responses of neurons. That's what's actually done. The problem is you need some time to do that. If you wait only 5 milliseconds, a neuron can only fire once every 5 milliseconds, so there's a spike or a no spike, doesn't tell you anything about the rate. And therefore I make a case here. I give you an image which is presented for roughly about 20 milliseconds, and the question I ask you is there a predator in this picture? So this is highly evolutionary relevant. Looking, watching, there we go. Was there one? Would you run away? I give you another one. You run away now? Did you see it? No, that was it. I show you again if you like. Okay, that's the first one. It's a lion in there, that's right. And what's here? There's a dog, exactly. So here are the two pictures. Is it a lion? I think it's a lion, mountain lion. So the question that I asked you was highly complex, yeah? This is not look at the picture, is there a picture or no picture? It's not is there an animal in this picture, but is there a dangerous animal in that picture? And obviously your brain is highly wired evolutionary to answer that question within 20 milliseconds. The problem with that is that 20 milliseconds is not enough to do any kind of rate coding or place coding or any kind of coding. In fact, this is a bit of a conundrum for physiologists or for neuroscientists to actually explain how the brain can do anything complex like that within a few milliseconds. Because for any kind of processing, you need time, and you haven't got that time. So the only real answer to that is that there's actually a different kind of process at work, which is called the timing code, the arrival time of the very first spike. So you look at the picture for an extremely brief time. All of the neurons in the retina, in this case, not an auditory example, all of the neurons fire. Only one spike. They can only fire one spike in 20 milliseconds. They're slower. They're even slower than the auditory system. And then this one spike, but coming from millions of neurons in the visual system at least, still carries that information. So coming up through the brain, in the visual system is the LGN and then the visual cortex, measures the arrival time. It's the only information that you really have, the arrival time of this spike, and derives that kind of complex information from it. So this is a population code. You need a lot of neurons for that. And there's nothing to do with rate or place or anything. This is just the pure arrival time. So that's my simple example to make it even more complex. And to end with this triangle, how is information, auditory information specifically coded in the brain? First of all, we have these temporal patterns, which are coded by the intervals between spikes. For example, that works if I give you a pure tone of 10 decibel and I ask you if you can hear it or not. Then you actually need some time to integrate that. And then you can argue, yes, there is a temporal code and there's a rate code and you need some time to integrate it, and that the rate code is a very good description of what happens if you hear a tone above threshold or below threshold. The second one is the connectivity or the place code. For example, for the frequency. So, for example, the pitch, low pitch versus high pitch, you can code with two ways, but one of the ways is the temporal, the tonotopic representation. Or I showed you another one, namely the question where the sound comes from, at least in the Jeffers model, is represented by the place of which neuron responds. It's place code. A third one that I just demonstrated is the time of arrival. For example, for localization in the brain. So time that one comes before that one would result in a temporal information. So these are only three aspects of it, of a very complex pattern here, obviously. Okay. Now let's come to something completely different. The brain. Oh my goodness, I'm running so out of time. This is a fresh brain. Still has its original colors. So the frontal lobe, this is descriptive now. 5 minutes of anatomy of how these things are called. Frontal lobe, parietal lobe, occipital lobe, temporal lobe, and the cerebellum below. They are separated by fissures. They're not usually in this color, and is also very, very much separated by function. And we investigate both now. This is called specifically the Sylvian fissure. Anybody wages a guess where hearing happens? Know that already? Say again? Temporal lobe, that's right. Here, specifically on that area where the mouse is. Which is exactly, pretty much by accident, I still don't know if that actually is a coincidence or not, is where the ears are as well. So maybe it's closest to the ears. But I do think that's an That's the coincidence. Okay, the cortex. Talking about the cortex, consists of grey matter surrounding the deeper white matter. We already know what the difference between grey matter and white matter is. Grey matter are the cell bodies that do the thinking. The white matter is the cabling between the areas of the myelinated axons that connects different areas. The anatomical division is roughly proportional to the 4 skull bones. So if a baby is born, it actually has an overlapping growing bones, so the bones still grow aside. So you've got 1, 2, 3, 4, which is associated to the 4, the frontal lobe, parietal lobe, and the temporal lobe. There's further division by the sulci and fissures, and the very deep ones, specifically the sylvian fissure, and the one up here, whose name I forgot, that separates the frontal and the parietal lobe. The cortex itself, into specific name gyri or lobules. The names sulci and fissures are equivalent to the gyri or lobules. They're just equivalents of the same thing. The cortex itself is between 1.5 and 4.5 millimeter thick. So imagine this is nothing. Cortex is, well, you know, cortex. The brain is 1.5 kilograms, but the cortex itself is where everything important happens. But this is only 1 millimeter on top. Well, 2, 3, 4 millimeter on top. So everything else is connections. Yeah. It also contains 80% of a brain's weight. Now this tells you a lot about why it actually looks like a shrinking walnut, because it needs to maximize surface. The cortex, Latin actually means surface, or outer shell, I think. I can't remember exactly. It needs to be big, needs to be large. It's sometimes said that it is the size of a football pitch. That's a lie. It's not quite as big. It's about 2 square meters, which is still very big. But it needs to be folded that often that it fits into our head. That's why it is just so thin and so what's the word? Folded. Consists of 6 horizontal layers. Functionally, I'm not going into that detail. Of which there are about 100,000 neurons in each square millimeter. Interesting is that the cortex is sort of the end and the beginning of all processing in the brain, because all the fibers from the brain stem radiate into the brain, into the cortex, and it projects downwards again through the thalamatic pathways as well. It is what we call the last link in the efferent pathway. But in reality, it's only the beginning of a process. But for us, it's the end point of where we understand what's going on roughly. And once it is in the cortex, it is obviously goes into the. We come to that in a second. Primary cortexes, and then it radiates out. So what does it do? Functional organization of the cerebral cortex. It is involved in thought, perception, and higher functions. What are higher functions? Everything that isn't the basic function. In humans, we also have a difference between the left and the right hemispheres. Specifically, usually in right-handers, our speech perception and processing happens on the left hemisphere, in about 95% of the cases. In left-handers, it's less often on the left side, but usually also most frequently. Whereas our right hemisphere is generally thought to be concerned mostly with pitch processing and perception. Sensory areas receive and process sensory information. Yes. This is not a specific hearing, but we usually have 3 different areas, namely sensory areas, motor areas, and association areas. Sensory areas are all the primary cortices. This is where all the information from the brainstem feeds up. So all the visual, the auditory, all the perceptual information. Then we have secondary, tertiary, and higher centers. We've got a primary auditory cortex, we'll come to in a second, surrounded by a secondary, surrounded by a tertiary, which means you've got a first station, then that projects into the secondary station, and so on and so on. It becomes obviously very complex very soon. The motor areas are all the ones that control motor function and sensory motor as well. And association areas is the fancy word for saying we haven't got a effing clue what's going on in there. So we call that association area, and they light up in MEG sometimes. But yes, in fact, there's a lot more known now than there used to be 5 and 10 years ago. There's a lot of money being spent on analyzing brain function, and I already mentioned the brain project that tries to simulate a brain. But there's another, it's an American project, has been going on for the last 5 years. It's called the Connectron, can't remember exactly. And they spend a few $billion on measuring all of the connections within the brain. And this is just not even functional, this is just anatomical. They have spent a lot of effort in measuring which area is exactly connected with which other area. And I don't know exactly the results, because this is just gobsmacking and breathtaking how complex the whole thing is. So what I tell you here is the very, very much boiled down version, obviously, of all of the real truth out there. So to understand what's really going on requires, at the moment, reading of a lot of literature. But it doesn't matter, we don't need to understand all of that. I'm going back to get a bigger overview picture. Okay. First important thing here, I'm going back 100 years, the mapping of the cortex. That is still true, because Brotman looked through a microscope and find that the psychoarchitecture of the 6 layers differs across the brain. So this is schematic, and he drew one famous picture, and he gave all of these areas different numbers, luckily, and not names. And these are all under the microscope different. So number 1 looks a little bit different from number 2, different number 3. That could be differences like the size of the cell bodies, or the number of synapses, or the thickness of the cortex, and so on and so on. And it turned out he didn't have a clue what was going on functionally, because they didn't have any way of measuring these things. Only much later it was then discovered that these Brotman areas are a very, very good representation of the function of these areas. Namely, later on, found out that 6 here, for example, premotor area, 4 motor area, somatosensic area, behind here taste area, and 41, 42, specifically interesting for us, auditory area, vestibular, and the visual area back here. So occipital lobe is mainly concerned with the vision. Okay. Specifically here, 41, 42, they're called the primary auditory cortices. They are involved in tasks such as identifying auditory objects and identifying location of a sound in space. It gets and processes all the information comes from the medial geniculate body, which I talk about. It's the thalamus as a mid-brain area between the auditory brainstem and the cortex. So effectively it receives all the auditory information from the brainstem, as we were talking about. It lies along the superior surface of the temporal lobe, but unfortunately for us experimentalists, it's largely hidden behind. So what you see here on the front is only a small part of it, because the main part is hidden on the other side. Which makes it quite difficult to access it for experiments. It's much easier, for example, to measure the occipital lobe, the visual area. So we're just unlucky in our area. They all project to the areas, to the secondary auditory areas, which is the area 22, which is this one, the Wernicke area. That's an interesting one for speech perception. It's only on the left side on the right-handers, and most left-handers have that on the left side as well. And how do we know about function? Well, in the general sense. And why is it important? Because function is often compromised because of strokes mainly. This must still be by far 99% of the reasons when it actually becomes compromised. people have a stroke. Strokes are very limited in space, but they can take out very specific brain functions. And if you happen to have a stroke in the area, the left side of area 22, you suffer very specific damage connected to your speech perception. So you have what's then called Wernicke's aphasia. You have a problem perceiving speech and very specifically for speech, but you can still hear and listen to music, for example, because music is processed on a different part of the brain, namely on the right side of the brain. Say again? Yes, it does. Very good. There's a guy writing books about that who's incredibly good. Forgot his name. I need to bring you the book maybe. He just collects stories of patients with weird damages like that, of which we know a lot, like these Wernicke and Broca areas as well. And there is a guy who cannot speak, but he can sing. Oliver Sacks, that's the one, exactly. I recommend reading these books. They're amazing people that had a stroke and suddenly learned to play the piano in no time. There was even a BBC program on that. But there's another guy, that's what I mean, who was unable to speak, but if he was singing, he had no problem. So he was running around singing, obviously, because he switches from the left-hand side of the speech processing to the right-hand side of the speech processing. It shows you how imaginative the brain is. So on the left side of the brain helps with generation understanding of individual words. On the right hand helps tell the difference between melody, pitch and sound intensity as well. It sends major track to 39 and 40. That's the association areas in the frontal lobe. The other one, the Broca area, so they're left and right of the primary auditory cortexes, is again left and right-handers and most left-handers, and damage produces a specific impairment of the production of speech, but not of the comprehension of speech. So these are effectively understanding speech and speaking speech, and this is from Wikipedia how people with the Broca and a Wernicke aphasia talk. So you can see a Broca aphasia, Monday, Dad, Peter, Dad, hospital, Wednesday, ba 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 ba. So problem completely making himself understood, but there is it's still comprehensible. They just have a problem to get a consistent sentence out and choose the right words and things. But obviously clear what this person tries to say. But somebody with a Wernicke aphasia has a problem, although it sounds completely fluent, it doesn't make sense because the words are the wrong words in the wrong time. So one is understanding, the Wernicke, understanding speech, Broca, producing speech. Okay, here's a very old, admittedly, but still very illustrative fMRI. fMRI is the method to measure on a relatively high temporal resolution, so within seconds, the functioning of the activity of brain areas. This is one specific patient, and this is the brain area that is active when this patient was just looking at words. So what happens is mainly the visual cortex lights up. So obviously he's looking at the words. When he's listening to words, the auditory cortex comes up, and Wernicke area lights up because he understands the words. If he's speaking words, the auditory cortex comes up, plus the Broca area more here in front, because that's the motor area that is necessary for speaking. Generating words without saying them doesn't affect the auditory cortex, but it does generate some activity in the prefrontal cortex, where obviously the thinking happens. So these are all aspects of verbs, or of language, but that you can see that different types of activity need completely different areas in the brain to work with them. Listening, looking, understanding, speaking keeps the brain active. This is my homunculus now, the one that sits behind your ears, between your ears, behind your eyes. Now this looks a bit funny, but it's a very good representation to understand a lot about the cortex. Namely, that's the surface of the skin. This has nothing to do with hearing, but it's actually equivalent to hearing. Namely, how much of your brain is connected or is active, concerned with this part of the body. So, what do you think, looking at this, is your most sensitive area? Is your lower lip and your thumb. And then the other fingers, your hands obviously, they take a huge area. Namely, this is a sagittal cut through the brain, where you can see all the representation. Here's the face, the lips are completely overrepresented. The fingers, thumb, blah 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 blah, hand, wrist, forearm, and then the rest of the body doesn't do very much altogether in terms of representation. What does it tell us? It tells us, first of all, the more brain you associate with a certain function, the better you become at it. Because you're much more sensitive in your thumb, not because your thumb is different from your upper arm, but because there's more brain concerned with processing the data coming from the thumb. Yeah? So if you have a stroke in the thumb area, here, your thumb would become less sensitive, but probably still more sensitive than say, your elbow or something like that. You see a lot of things here. There's also a neighboring relationship. So everything here is neighboring. Forearm next to wrist, next to hand, next to little, ring, middle, index, thumb finger. But then something weird happens, namely here, at some point this two-dimensional to one-dimensional mapping doesn't work anymore. You have to make a jump. And the jump happens between the thumb and the eye. And there are very good described examples where people do brain surgery, and suddenly you have a mixture between the sensory input from your thumb and your eye. So you hurt your thumb and actually you feel it up in your eye. That also tells you if you lose some of the function, it can be recovered by other areas. This is the same principle as tonotopy in the ear. This is the muscle, so it doesn't show anything of the ear. But the tonotopy that we encountered on the basilar membrane is the same principle as the neighboring relationship between the shoulder and the neck. They're neighboring here, so they're neighbored on the brain. And the high frequencies and low frequencies are neighbored in the basilar membrane, so they will be neighboring on the brain. Yeah, and this is how I leave it now. And if we have time, go more in the auditory aging. But as I said, this is more a descriptive, high-level description of it. But this was more important today. This endeth this lecture.